Hello, welcome back to our channel. Today we are going to discuss about calorimetry. It is the part of the thermal properties of matter. In previous videos I have completed expansion of gases, expansion of liquids and expansion of the solids, and now we are going to discuss about what is the calorimetry. Already you know that heat is a form of energy. Temperature, degree of hotness or coldness is called the temperature. But here how to measure the heat? You know that heat is a form of energy. Here we are using that heat is measured in calories, in CGS system, and joule in SI system. And you remember that 1 calorie equals to 4.2 joules. You must remember that 4.2 joule. Then we focus on specific heat. What is the specific heat? It is represented by S. When we are going through the molar specific heats, we are taking Cp or Cv, like that we are taking. So, but now in this, what is the basic definition for the specific heat? See, the amount of heat energy required to raise the temperature of 1 unit mass of the body through 1 degree centigrade. That is called the specific heat. What is the meaning for this? Suppose you are taking, this is one of the material. We want to raise the temperature of 1 unit mass, not entire system mass. 1 unit mass, that too, how much temperature we should increase? 1 degree centigrade. That is called the specific heat. It is represented by S. So 1 unit mass means we are taking 1 by M. It should be right dQ by dt. dQ by dt. So how much energy is, heat energy is required to rise the temperature of 1 degree centigrade of 1 unit mass is called the specific heat. And what is the unit for this? This is the joule kg degree Kelvin in SI system. And in CGS system, what we are taking? Calorie, gram, degree centigrade. But how to do the conversions of this one? See, suppose we want to convert 2 calorie gram degree centigrade into SI system. So 2 is 2 only. Instead of calories we are taking 4.2 joule, and gram is the 10 to the power of minus 3 kg, and degree centigrade and degree Kelvin, both the scales difference is same. That's why we can take it degree Kelvin. Finally it should be right 2 into 4.2. When 10 power minus 3 is comes up, we can write it 4200 joule kg degree Kelvin. So this is the unit. So whenever you want to convert specific heat from one unit to the another unit, they are giving like CGS, we want to convert into MKS or SI system. Then what we are doing? Instead of calorie, we are writing 4.2 joules. Instead of grams, 10 to the power of minus 3 kgs. Then when it comes up, directly we can multiply with 4200. Then easily we can convert. Then come to this point. From this we can write the expression dQ equals to M into specific heat into change in temperature. From this we can find out the change of heat energy or flow of heat energy also we can able to find out. In future thermodynamics we are using this concept. So this is the specific heat formula, and these are the units for this. Now we are focusing on heat capacity. What is the heat capacity? It is represented by H. See, the amount of heat energy required to raise the temperature of the body through 1 degree centigrade. We didn't mention any mass. We are taking one system. We want to raise the temperature of 1 degree centigrade. That is called the heat capacity. So H equals to, simply we can write it dQ by dt. dQ by dt. See, S equals to unit mass we are taking. We didn't take the unit mass. Then how to find out what is the unit for this? You can say joule per degree centigrade or degree Kelvin. Then in CGS system it should be right calorie per degree centigrade. Then we focus on relation between S and H. See, S equals to, we should write it H by M. From this H equals to mass into specific heat. This is the relation between them. So when we are using this specific heat concept, we want to increase the temperature of the one body. We are using this. We must consider the specific heat of that one. For water, it is 1 in CGS system, and that is 4200 in SI system. Like that for ice also 0.5. So like that we can take the steam also. So different physical, like copper is different, iron is different, silver is different. Different materials are having the different specific heats, and this is about the heat capacity. Now we are going to the latent heat of latent heat. What is the latent heat? At constant temperature, if the system is changing from one state to the another state, like from liquid to solid, solid to liquid, then liquid to vapor, vapor to like liquid. So here at constant temperature it happens. This concept is called the latent heat. So latent heat, what is the formula, what is the definition for this? Latent heat is represented by L. The amount of heat energy required to change the state of the system at constant temperature is called the latent heat. Simply we should write it per unit mass, not for entire system. The amount of heat energy required to change one unit mass of the system to another system, another state, that is called the latent heat. Simply we can write it L equals to dQ by M. Here also we are getting change in heat energy is M into L. You should remember that latent heat of ice equals to 80, that unit is what? Calories per degree centigrade. If you want to convert, already you know how to convert this one. But here there are two latent heats we should consider. One, if the body is, or if the system is changing from liquid to the solid, that is called the latent heat of fusion. Either freezing or melting also, both we should consider that latent heat of fusion. Like that if it is converting from liquid to the steam or steam to the liquid, that is called the latent heat of vaporization. So this is about the latent heat. We should consider, we have to consider this is the at constant temperature only it happens. Then triple point of water. What is the triple point of water? At particular temperature and pressure, we can observe three states of water: ice, then water, then steam. That is called the triple point of water. At all conditions we won't observe that, but where we should observe that? At particular temperature 273.16 degree Kelvin, and the pressure is 0.006 millimeters of Hg only, it happens. This is called the triple point of water. Then we focus on transfer of heat. How many methods are there to transfer the heat energy? There are three methods to transfer the heat energy. First one is the conduction, second one is the convection, third one is the radiation. In the case of conduction, take while iron rod, you feel this is the iron rod, we provide the heat energy. But when you touch this side also, we feel hot. Why? The heat is flowing through the vibrating particles from one end to the another end. This is called what? This is called the conduction. But in conduction, how to find out the rate of flow? Look here. We are taking one slab here. Area is A and length is how much? L. Here the temperature is theta1. Here the temperature is theta2. When the heat is flowing from one end to the another end, here theta1 is greater than theta2. Here the heat energy is directly proportional to temperature difference, then area of this one, then it is directly proportional to the time also, but it is inversely proportional to the length. From this, when we are taking Q by T, rate of flow of heat is directly proportional to theta1 minus theta2 into A by L. Here we are getting one constant, that is called the temperature coefficient. So it is represented by K into A into theta1 minus theta2 by L. Temperature coefficient of resistance. From this, what is the expression for K? We can write it K equals to Q by T into A divided by temperature gradient theta1 minus theta2 by L. So it should be right ratio of rate of flow of heat per unit area to the temperature gradient is called the temperature coefficient of resistance. It is represented by K. From this you are getting that thermal resistance also. What is the formula for thermal resistance? You know that normal resistance is it opposes the flow of electric current, but thermal resistance is simply we can write it R equals to L by Ka. Thermal resistance R equals to L by Ka, and it should be right theta 1 minus theta 2 divided by Q by T. Temperature difference to the rate of flow is called the thermal resistance. So otherwise you can take it L by Ka also thermal resistance. There are two conditions. Based on this we can find out what is the series and parallel combination of thermal resistance and temperature coefficient of resistance. Look here, we are taking like different slabs are there. First one is the K1, length is L1, this is the K2, length is L2. We are connected in series like that Kn and Ln. Here thermal resistance what we are taking, effective resistance is R1 equals to R equals to same R1 plus R2 plus so on R3 we are taking. But temperature coefficient of resistance what we are getting 1 by K1 plus 1 by K2 plus and so on Kn, like that you are getting. Like that in parallel we are connecting different slabs are like that. So in this case what we are taking 1 by Rs, thermal resistance is the 1 by Rp. We are getting 1 by R1 plus 1 by R2 plus and so on 1 by Rn. But temperature coefficient we are getting K equals to K1 plus K2 plus and so on Kn. So you must remember these formulas in the case of conduction. Then we are going to discuss about the second method is what? Convection. So what is a good example for that? Look here, when we are providing the heat energy to the water container, these water molecules are taking the heat energy, then density will becomes less and it will go up. Cool water is coming down. So due to the movement of that water molecules, the heat energy is transferring from one place to the another place. Here actual movement is there, but in conduction there is no actual movement of the particles, that is through vibrating particles, that's all. But here due to the actual movement of the particles, heat is transferred from one place to the another place, that is called the convection. But there are two types of convections are there. One is the forced convection, another one is the natural convection. Generally at homes what ventilators we are providing just below the roof. Why? Natural air is, cool air is coming through the window, then hot air density is less, it will go up, it will go through the ventilators. Then forced convection, now these days we are using the airs. Forcefully we are taking the hot air and we are sending outside, that is called the forced convection. The next one is the radiation. In that heat transfer, third method is the radiation. What is the radiation? See, for conduction and for convection we require the medium to flow of heat energy. But in the case of radiation, without any help of that medium, it can able to propagate from one place to the another place. That is called the radiation. You know that sun rays are coming from sun to the earth. In between there is no medium. So this type of heat transfer is called the radiation. So in this radiation, we have to remember that what is the black body, what is the absorption coefficient, what is the emission coefficient, all this. Absorption means how much radiation we require to absorb the 1 unit area of that body. Radiation means how much it is emitted through 1 unit area is called that emission. Absorption by emission is called the emissivity, it is represented by E. So after this, that many people they have given that how we are calculating the rate of flow of heat energy. First person is the Stephen's law. Stephen's law. According to that, what he said, rate of flow of heat energy is directly proportional to 4th power of absolute temperature. It is for black body. If it is not black body, we can take it E equals to, like we are getting one constant E into sigma into T to the power of 4. Here sigma is called the Stephen's constant. Like that, Stephen's Boltzmann's law, two members are there. They have corrected this. this E is directly proportional to T power 4 minus Ts power 4. T power 4 is the temperature of the body and Ts is the temperature of the surroundings. Then we are getting some constants. If it is not black body, we should consider area. We can consider this one and sigma T to the power of 4 minus Ts to the power of 4, like that. The next one more thing from this, after this Newton's law of cooling. What he has given, that rate of flow of heat is directly proportional to temperature difference. Then here we are getting dq by dt equals to one constant, that is the minus b into t minus t naught. After this, instead of dq, just now we know that ms by dt, like minus b into t minus t naught. So like that we can use the Newton's law of cooling also. So this is about the radiation. Better you have to revise all these concepts and do that previous year's problems. Otherwise, already you have practiced during the first year. Once you can go through this one, then you will be perfect in this chapter. Thank you everyone. Please subscribe my channel.